Greetings to all. This is Mrs. Sunita TC, Selection Grade Lecturer, Department of PLC, Government Polytechnic, Srirangapatnam. Welcome to ARM Controller. In the previous session, we have discussed risk design philosophy, where we saw how instructions, pipelines, registers, and load store architecture decided the architecture of RISC type of processors. The instructions had to be kept simple with single cycle execution, and it had very few addressing modes and fixed length instructions. Coming to pipelines, the instruction execution would be broken down into smaller units so as to be executed in the pipeline. Say fetch, decode, and execute operations, which would complete in one pipeline stage, thus maximizing the throughput. Then registers. Having more registers means the memory dependency will reduce, and this will improve the code density and execution speed. Finally, load store architecture implies that the data transfer between memory and register is by explicit instructions load and store. These features are the important points of RISC design philosophy. The next topic that we discussed was ARM design philosophy. We saw that ARM processor design was highly influenced by the requirements of the embedded system, and thus a smaller processor was chosen as it reduces the power consumption and extends the battery operation. The second point was high code density provided by this appropriate design of the system. Ability to use slow, low-cost memory devices would reduce the final cost size of the embedded system. Thus, it was seen that ARM is not a pure RISC architecture, but one which emphasizes effective system performance and power consumption rather than speed. The last topic was the selection of instruction set for embedded systems. ARM instruction set also has been specifically designed so as to be suitable for embedded applications. It does not conform to purely RISC architecture and deviates on the following points so as to be able to be applicable for embedded systems. The first point is variable cycle execution for certain instructions. So some of the instructions will not complete in one single cycle. Second point is inline barrel shifter leading to complex instructions. So having this hardware generates complex instructions which will provide high code density. The next point was the 16-bit thumb instruction set inclusion. So this again was to improve the code density and performance. The next point was conditional execution of instructions. Again, this reduces branch instructions and leads to high code density and improved performance. The last point was enhanced instructions where DSP instructions were added to the standard ARM instruction set so as to support 16-bit by 16-bit multiplication and saturation operations. This lent the ARM processor to be used for DSP type applications. In today's session, we are going to discuss about embedded hardware and AMBA bus protocol. Embedded systems are mainly used to control and monitor different devices. These could be simple sensors monitoring temperature or a toy car, or very complex real-time control systems used on space probes or missiles. Be it a simple or a complex embedded system, they all use a combination of hardware and software components. Here, each component will be chosen for its efficiency, and if applicable, it is designed for future extension and expansion. This figure shows a typical embedded device based on ARM core. So here each box represents a particular feature or a function, and the lines that are connecting the boxes are the buses that carry the data. The ARM device consists of four main hardware components: the ARM processor, the controllers, peripherals, and bus. ARM is the execution engine that processes instructions and manipulates data and controls all the devices interface to it with a bus. The ARM processor's main function is to control the embedded device. Now, how to choose a processor for a embedded system? There are different versions of processors that are available to suit the desired operating characteristics of the particular embedded system. So here, the embedded system, if it is a simple one, we can go for a very simple system, and if it is a complex one, you can also have the choice of choosing a very complex processor. So there is a wide choice available to be chosen for the operating characteristics of the embedded system. Along with the processor core, there are memory management unit and cache present on the chip. The next hardware block is controllers. Controllers are important functional blocks in a system. ARM has consciously decided to keep the processor core small and has separated the function of managing the memory and interrupts in the form of dedicated controllers to perform these functions. There are usually two controllers found in ARM processor core. They are interrupt controller and memory controller. The next blocks that are seen in the block diagram are the peripherals. These provide all the input-output capability external to the chip. They also decide the uniqueness of the embedded device. This is because Peripherals are chosen to provide input-output interface. This depends on the particular application, and thus peripherals provide the uniqueness in the embedded system. These peripherals may be very simple serial communication devices where single bit of data is transferred, or it may be more complex wireless devices which will transfer the data. In ARM, all peripherals are memory mapped devices. That is, peripherals can be accessed just like a memory device. And programming of these peripheral devices is also made very easy by providing a set of memory addressed registers. So if you access the base address and with the help of the offsets, you can access any of the register that has been dedicated for this purpose. The fourth component found in embedded systems is the bus. This bus is nothing but a group of wires to carry signals which is used to communicate between different parts of the device. Interrupt controller. An interrupt controller provides a programmable policy which allows the software to determine when a peripheral can interrupt the processor at the specific time by setting the appropriate bits in the interrupt controller registers. Usually there are two types of interrupts controllers for ARM processor: the standard interrupt controller and vector interrupt controller. Standard interrupt controller. This provides maskable interrupts. Maskable interrupts means the interrupts may be enabled or disabled, that is masked or unmasked. The interrupts will be serviced only if its bit is unmasked. If it is masked, even if the interrupt occurs, it will not be serviced. The interrupts may be enabled or disabled by setting a bit in the respective interrupt registers. So this is standard interrupt controller which allows the masking and unmasking operation of interrupts. The second interrupt controller is the vector interrupt controller. This controller assigns a priority to all the interrupts associated with the processor. So, depending on its importance, it will be assigned a higher priority. Also, the address of the vector or the interrupt service routine or handler address will be assigned to each of these devices which require the services of the processor. The vector interrupt controller asserts an interrupt signal to the processor if the priority of the new interrupt which has arrived is higher than the currently executing interrupt handler. If its priority is less than the currently executing interrupt handler, it will be kept pending until the higher priority interrupt is completed. Depending on the type, the VIC will call the standard interrupt exception handler, that is, it will load the address of the handler for the device from the WIC, or it may cause the code to jump to the handler for the device directly. So that is dependent on the requirement. How the address service interrupt service routines address is provided will be decided by WIC. So it has two options. One, to load the address of the handler from the vectored interrupt controller, or to cause the core to jump to the handler directly. Both are possible. In memory controllers, different types of memory like static RAM, dynamic RAM, flash RAM can be connected to the processor bus. On power up, the memory controller configures certain memory devices to be active, and these devices allow the initialization code to be executed. With this, we conclude the discussion on embedded hardware. The next topic is AMBA protocol. In personal computers or desktop computers, the processor core and peripherals are interconnected by a bus. A bus is a group of wires to carry signals. The bus connects any two devices mechanically and electrically. These devices are available on the motherboard in the case of the personal computer or desktop computers. The processor IC, the peripheral ICs are all present on the motherboard, and it will be connected by the bus. So this is known as peripheral component interconnect or PCI bus, and is used to connect devices like video cards, hard disk controllers to the x86 processor bus. This technology is applicable only for external or off-chip devices, that is separate ICs. The bus terminology: in a bus, there are usually two classes of devices attached. One is known as master devices. The other group is called as slave devices. A master device or bus master device is a logical device which is capable of initiating data transfer across another device connected in the same bus. Usually, the core is a bus master. Slave devices are those which will only respond to a transfer request from the bus master device. These devices cannot initiate or start a data transfer operation on their own. So they can only respond to a request from the bus master device. So these devices are called as slaves. So peripherals are usually bus slaves. In case of embedded devices, the core and the peripheral are integrated on the same IC. To interconnect the core and the on-chip peripherals or embedded peripherals, we need a different bus standard other than PCI. This is where AMBA protocol comes into picture. AMBA or Advanced Microcontroller Bus Architecture is an on-chip bus architecture. This was introduced in 1996 for the ARM processor core. So we have come to the slide which was earlier shown for the embedded hardware once again. So as mentioned earlier, the lines are nothing but the bus which is used to connect the various devices, on-chip devices. So here you can see we have the ARM core, the interrupt controller, memory controller, and some of the peripherals, that is real-time clock, serial UART, Ethernet, and others. Now we also have some bus components which are available here. One is it's the bus. Then we have the external bridge, AHB APB bridge, and AHB orbiter also. These are all belonging to the bus or AMBA bus architecture. And here we have two distinct regions. One is called as the high speed region, AHB or ASB it is called as. And the one which comes below AHB APB bridge in the diagram is the APB bus, which is slower and normally operates at 1/4 or half the speed of the AHB or ASB bus. Now, what is AHB and ASB? When AMBA was introduced in 1996, the initial design had two components, ASB, Advanced System Bus, and APB, Advanced Peripheral Bus. The improved version of AHB was later introduced, and this is ARM High Performance Bus and APB. The ASB design used the traditional bidirectional bus to which tri-state devices were connected. So bidirectional bus means the lines can carry the signal in either direction, that is inflowing or outflowing signals. And tri-statable bus or devices means the devices can be in low impedance state or high impedance state, or in the logic 1, logic 0 and high impedance state. AHB or the advanced bus uses a different concept, that is centralized multiplexed bus scheme, where all the devices are connected through a multiplexer which will speed up the process of accessing the devices that need to communicate with each other. So this scheme provides for higher data throughput, and it supports higher clock speed of and 64-bit or 128-bit wide bus also. There are two variants available in AHB, multi-layer AHB and AHB Lite. Again, when AHB was initially introduced, it supported single bus master, and these two variants, that is multi-layer AHB and AHB Lite, were later on introduced. In multi-layer AHB, it supports multiple active bus masters and is suitable for multiple processor systems. Higher throughput range is also achieved by parallel operation because of the presence of multiple processors in the system. It supports same protocol for the master and slave devices that have different interconnects also. AHB Lite is a subset of the AHP bus and is limited to a single bus master, and it is designed for applications which do not require full features of the standard AHB bus. APB, that is Advanced Peripheral Bus. The ASB or AHB connect processor and the high performance devices and is a high speed region. Whereas the APB bus connects the slower peripherals together, and this slow speed region of APB can communicate with high speed region AHB ASB through the bridge. So bridge is the device which connects the high speed core and memory devices with slow speed peripherals. The next bus device is arbiter. A bus arbiter circuit resolves bus contention between multiple bus masters. If two or more bus masters request for the use of bus at the same time, the arbiter resolves this contention and allocates the use of bus to the one with the higher priority, or the bus master having the higher priority will be allocated the use of bus. This will be decided by the arbiter device. In the bus, we have two architecture levels defined. The first level covers the physical level, covering electrical characteristics and bus width. It may support 16-bit, 32-bit or 64 bits bus. The second level deals with protocol, the logical rules that govern the communication between the processor and a peripheral. AMBA provides a standard bus interface and is very popular in a large number of peripherals. Why is AMBA popular? So this is because the hardware designers have a wide choice of tested and proven peripherals for use in a device. This is because the AMBA protocol peripheral designers can reuse the same peripheral in multiple projects. They do not have to start from scratch the design of the peripherals. Instead, once a peripheral has been designed, tested, it can simply be connected to on-chip bus without having to redesign the interface, whatever is the processor architecture. So if it conforms to AMBA protocol, then you can simply plug and play this interface, and this provides lot of flexibility in the design. This also provides lot of choices or availability for the designers, and it also reduces the overall design time, that is time to market is reduced. So with keeping in mind all these factors, many of the peripheral designers design peripherals with AMBA protocol, and thus the availability of the large number of peripherals. So with this, we have come to the end of this session. So some of the descriptive questions that can be based on this unit is, Explain the hardware components used in an ARM-based embedded device. Explain memory controller and interrupt controller. Explain AMBA bus protocol. Explain the architectural levels of bus and explain the AMBA bus variants. So, some one word question answers. The four main hardware components seen in an embedded system are processor, controller, peripherals, and bus. Second one, two commonly found controllers in an embedded system are memory controllers and interrupt controllers. Dash devices provide the input output capability external to the chip. Peripheral devices provide input output capability external to the chip. This is a logical device capable of initiating a data transfer with another device connected to the same bus. So it is a bus master. This device only responds to transfer request from a bus master device. Such a device is a bus slave device. AMBA stands for, the acronym AMBA stands for Advanced Microcontroller Bus Architecture. The next question is, Dash is a on-chip bus architecture used for ARM processors. AMBA is the on-chip bus architecture used for ARM processors. The two variants of AHB bus are multi-layered AHB and AHB Lite. Dash is a subset of AHB bus limited to a single bus master, AHB Lite, and Dash allows multiple active bus masters. AHB bus allows multiple active bus masters. These were the reference materials that were made use of in preparing this study material. Thank you.